methanol, kind of follow that pattern when you're doing these strong electrolytes, because they're going to come back up on your final. Follow that pattern of cut out the strong acids, cut out the strong bases, cut out the salts, and then whatever this other stuff is left, if it doesn't fit into one of those three, it's this other. Okay, and that's what column that methanol would have fell under. So it has no metals, it's all nonmetals, so it can't be ionic, it has to be covalent. We know it's not a strong acid, right? No acidic hydrogen in the front. We know it can't be a strong base because it's not on the strong base list. Now this could have threw you for the OH there, but what does even a weak base, what is the positive half of that have to be? It has to be a metal, right? The only exception for that is a weak base that's ammonia. Every other base, even if the OH would have threw you, this CH3 had to be a metal. It had to be a titanium or an iron or something outside of one of those. So once you'd eliminated these four left, and we've already said it's not a metal as the cation, so it can't be that salt, it had to fall under that other. If it falls under that other, and you know only your strong acids, strong bases, and salts are strong electrolytes, would that methanol be a strong electrolyte? No, right? It's not gonna dissociate well. It's gonna have a two-way arrow on that methanol when it dissociates. And how about the ammonia? How did y'all do on this ammonia here?
Bad. So it was solid.
Bad, okay. So ionic or covalent? Covalent, all nonmetals. Does it have acidic hydrogens in the front? No, so it can't be a strong acid or a weak acid, right? No acidic hydrogens. Does it have an OH group? So at first you would think, okay, not weak base or strong base, but our only exception for our weak bases here were ammonia. Just like hydrogen is the exception for everything, ammonia is the exception for weak bases. It's the only base that we have that does not have an OH group. But we consider it a base. We consider it a base because when it ionizes in water, the water is actually forced to act like the acid, which makes the ammonia the base here. And it acts like that base because it produces that hydroxide. So even though it doesn't have hydroxide in its formula, when it's exposed to water, it produces that hydroxide, so it acts just like a base. But because it's a weak, it's going to have that equilibrium. Was there any other ones that were tricky here? And would your NH3 be a strong electrolyte? Yes or no? No, because anything weak or anything other is going to be a weak electrolyte, so it's not going to be a strong electrolyte. Name? Name?
Jacob.
Jacob. Last name?
Gregory. We cursive.
Oops, sorry. Oh, that's my bad. Okay. Were there any others that kind of threw you on this chart? I know this chart kind of seems a little overwhelming at first, but if you really do break them down individually and carry them down this hierarchy, if you carry them down strong acids, strong bases, if they're not a strong acid, not a strong base, they could be a weak acid or a weak base. But some of these you can eliminate immediately when they don't have those acidic hydrogens, right? And then your salts always have to have metals to be a salt. Just be careful with your ionic and covalent and how they behave. Yeah, the others always throw people. Did okay on that balancing though? Did okay on this balancing? What was this?
1, 3, 2, 1, 6.
What type of reaction was this?
neutralization. Wait.
So you start off with two compounds, and you end up with three. Yes. The only way you can end up with more stuff in different pieces than what you start with is something got broken up into little pieces and it wasn't able to get back together. So this was a decomp reaction, and sulfuric acid is actually oxidizing this potassium 4 or potassium 6 cyanide there. So you get some iron sulfate, some cyanic acid, and some salt, some sodium sulfate, some potassium sulfate salt. Name.
What?
Your name.
Madison Stewart?
You're welcome. Just leave it back there in case someone else comes in. They can sign in. Okay, so how about these reactions? How'd y'all do on these reactions? So what about this first one? Hydroiodic acid reacting with water to make hydronium and just iodide anion. What is that? Ionization. What about this one here?
Dissociation.
Dissociation, right? The only difference between these two, they both make charges, but in this one, water is not a reactant. In dissociation, water is never a reactant. It's used to facilitate, but it's not a participant. So it's one of our intermediates and we drop it out.
Is it disassociation because it still has the charges?
Yes. But those charges normally when they're dissolved, unless you take the solvent away, they won't recombine. So it's like you can keep salt dissolved in water as long as there's water there. When you take all the water away, then the salt has nothing else to pair with, so it'll go back to itself. But the water is what's facilitating the salt to break apart in the first place. What about this one? Combination. Two separate things combining to make one new compound that does not look like this or this, right? It's something new in a new arrangement. What about this one? Single. Cadmium kicking out copper. This one. Combination. Two separate things recombining to make a new, different type of compound. What about this one? Double. Cadmium. Carbon switching. Right? The anions didn't, nothing happened with the anions. We didn't change, right? Nothing compound-wise changed. You didn't make a carbonate or anything like that. You just switched your metals there. So that's going to be a double displacement. Since this reaction happened, one of those were a solid. Which one do you think would be the solid? Just thinking about kind of what you know about cars and things like that. What is this normally? Normally a gas, right? And in reactions, it'll normally evolve as a gas. So this guy was normally going to be your solid. He's going to be your solid there. What about this one? Decomp, right? Started with one thing, ended up with two different pieces.
I have a quick side question. What's the best way to start preparing for the final?
Tests.
Going over the tests?
So your tests are the best metric you have for what's going to be on the final. Because there's no material outside what we have covered that is going to be on that final. Now, it's going to be in different ways. Like, different teachers can ask a question differently. So like, if he did not get to put this question on the test, but another teacher did, right? Because it's a combination of all the teachers' questions. They may ask this question differently, but if you understand the concept, you should be able to still get the question, right? If you know something's a strong electrolyte, no matter which way we ask it, you're going to be able to recognize, hey, this is a strong electrolyte.
So basically just daily review the tests.
Well, yes and no. I wouldn't say hammer in the things that you did well on. Really hammer in the things that you missed points on, because if you don't review them, you're obviously going to miss points on them again. And the final is no partial credit. So it's multiple choice and right or wrong. And then kind of brush up, just kind of a quick review on the things from earlier on in the semester, because guarantee you're not as well as you were at the beginning of the semester on a specific E. You could kind of like stumble through a problem, but like just doing a couple of examples, you're going to get back how to set it up and how to.
We just did that in the lab, and I was like,
Right.
I don't know.
And it's just because we've had 9 weeks between that, right? 9 weeks
It was
between
like
when we.
August.
Yeah, 9 weeks between when we covered that and now. So, we didn't expect you to remember how we did and what we did it and, all that. So, doing those and you're going to see what mistakes you made, and you can help yourself prevent yourself from making those mistakes. What about this last one? It was actually the only type of reaction you had on that. Yeah, the neutralization was the only one you had on there for it.
That's a combination if you counted it right.
Yeah, I do.
Actually, the same thing. Why?
Bond two things in
But in a neutralization, what is another component of a neutralization that we don't have here?
H2O.
Yeah.
The water, right? Because there's no acidic hydrogen. There's acidic hydrogen there. There's acidic hydrogen there, but there's no OH present, right? There's no presence of OH. But what will actually happen is this ammonia, because all of this is in water, right? All of this is broken down in water. So this ammonia here is going to react with excess water and make some OH. So even though we don't have it specifically happening in this reaction, other ammonias are going to be reacting with other water molecules and making OH. And it will make water, but just not in that specific reaction. Dylan? Nick. Not even close.
Yeah, I bond it probably. Yeah, question that it is.
What's your last name?
Pie. It was. Yeah, I bond it.
But the ammonia will react with excess water and make excess hydroxide, which will make another product of water. So you will have that water in there. But what is this? This is a what? If it'll dissolve in water, we know this will dissolve in water, right? Because it can go in the reverse. Weak, so it can go in the, this strong forced it, but this is a what? A salt. So that salt can dissolve in water, so it fits either one, because you started with two things and only ended up with one. So you combine these two together, and for whatever reason, as this sits, that can't get back apart. We got to have that water to break that apart, so it fits both of them, and that's why. Neutralization, because you neutralize an acid with a base, and it will fit that. And it can also be a combination because you started with less stuff than you ended with.
I have another question.
Less products than reactants.
Are we going to get a review packet for the test, or not really?
For the final?
Yeah, is there
He will have a final review on there. The problem with the final review, it's things that he knows is on the test. So that's things that he submitted. So that's why I say your tests are your best resource, because that's a culmination of the material, and then you can use your tests and compare it to your final and see what is there only really one thing that he emphasizes on specific heat, or is there, did all the teachers like specific heat, so there's 2 or 3 questions? You see what I'm saying? What was the general consensus of the final? Because it's
There's still test 5 and then the final.
mm-hmm. You got one more test, and then your final. And I'm going to. When do you all want to break for Thanksgiving? Is it? We have Wednesday. We have the Wednesday before Thanksgiving.
Thursday
Yeah, I
through
think it's
Sunday.
Thursday through Sunday. Okay. And depending on how your test is going to fall, we're going to have a review that weekend. I don't know if people are leaving town, but we're going to try and have a review that weekend, either Saturday or Sunday. And I'm going to post a doodle poll link on the course news at the top heading, where you can go on there, put your name on there, and submit the times that are best for you that day. And we'll do like a block, like 2 or 3 hour, and you can come in and leave and ask questions or whatever it is you're needing. I'll get it reserved for this room, though. But I was going to go ahead and tell you all about that. You're Nick. Are you Nick? No. Zach. Don't feel bad if I don't know your names. I got up this morning. I thought it was still a dream. Zach.
Zach Wood.
Wood. So this one was just a molar conversion. We were told, or we were asked, how many atoms of sodium were present in 150 milliliters of 3.25 molar sodium sulfate solution. So your general equation for molarity is equal to your moles of your solute over the liters of your solution. So your molarity in this case was 3.25. Your moles is actually what we're trying to find, because from moles we can get to atoms, right? Avogadro's number. So our moles is what we want to try and solve for here. And we were given the volume, but we needed it in liters for the denominator, so this needs to be 0.150 liters. And I'm just going to solve that. I don't know what that comes up to be. Okay, I'm coming up with 3 sig figs. I'm coming up with 0.488 moles. And so our solute in this case is going to be our sodium sulfate. So you actually don't need to use your molar mass on here, right? It's already in moles for us, so we don't need to use our molar mass, but we do need to get down to atoms, okay? And this first piece is going to get us to molecules, because for every mole of sodium sulfate, there's a group, should be a 2, but yeah. There's a group of atoms there, a large group of atoms. So when you do Avogadro's number, what that gets you is molecules, okay? The molecules of your sodium sulfate. And then from each molecule, you have 2 sodium atoms present in each molecule. Okay, you want to make sure your units cancel for that. And that should leave you in atoms of sodium. So for that one, I'm getting 3 sig figs, so 5.87 times 10 to the 23rd atoms of sodium. Give or take a little bit for rounding if you got near that. Any questions about that? Any questions about how to do that? Difficulty with doing that. The part that may have threw you off was this last part here, was this atoms. Some people just go straight to Avogadro's number and they think it's always atoms. Well, it's dependent upon what you're starting with. So if you're starting with a compound, when you use Avogadro's number, it's going to get you molecules of that compound. And then you've got to break it down into exactly what you're wanting there. Okay. Number 5 was actually right off your study pack. It's actually a combination of your study pack and your exam, practice exam. What may have thrown you off on this one is you didn't use your more concentrate. But if you look at PSI, we actually did this problem, but it wasn't the right numbers, but we actually did this problem. So your formula is always your more concentrate, your more dilute. So in this case, what you were keying in on here is this concentration is the one you actually started with, right? You started with the higher concentration, and that's the volume that you were trying to solve for. You're trying to solve for the volume of the concentrate, knowing that you had produced this solution. Sorry, I used the wrong volume. Oh no, that's right, 500 liters. He didn't ask for it in liters, but I just didn't have it. So the volume for this, more concentrate on my answer will come out in liters. You may have done it in milliliters. Perfectly fine if you did, because he didn't specifically ask in the problem liters or milliliters. He just said volume. If he said volume in milliliters or volume in liters, then you need to have it in that unit. Okay. Yeah. Sorry. Oh. Number 6. So you're given the reaction and you're asked to find the molecules of the dihydrogen sulfide that could be produced by reacting this 5 grams of copper iron sulfide with excess. So when we say this excess here, what is this not going to be? Limiting reactant problem. If we told you that there's X number of HCl and X number of copper iron sulfide, and you see that both of them are reactants, you're thinking about making hamburgers. If I'm making hamburgers, I'm going to run out of bread or cheese first, right? Because for whatever reason, hamburger buns come in packs of 8 and cheese always comes in like 20s or something like that. So they never work. But this would be a limiting reactant problem in that case. Okay, so you're given your 5 grams of your copper iron sulfide. And we want to get that molar mass. Does someone have that off their test? When who has their test back?
183.525.
And that'll be grams per mole. Okay, so then once you've got your quantity here in the moles, we can move through this chemical equation up here. So we were going from our copper iron sulfide, so we want the coefficient for our copper iron sulfide is what? 1. And then what we want to go to is the coefficient for our dihydrogen sulfide. So what's that? 2. And since it was already in moles, what can we go straight to? Avogadro's number. Don't even got to change the units. Don't even do anything. Wonderful beautifulness. Okay. So that's how it should be set up. Does anybody have anything different than this setup and got it right?
Wait, what do you ask?
Oh, you have this set up? You don't have this set up? Do you have any questions about that?
Not on my test back.
No, I'm trying to think of your name, but I have not.
Kristen.
No, I wouldn't have got it. And see, it would throw me off. Are you the Scott or the Keck?
Okay.
The Keck. See, there's two, and one of you is an I and one of you is an E. Always throws me off. Especially when I'm doing like the data of like who signed in. This. Okay. So number 7. So 7 was another molarity problem. And we were asked to find the volume. Since it doesn't specify, you can do it in milliliters or liters. It's going to be easy for us to just leave it in liters, and that's what's going to come out as. So what volume of your hydrochloric acid could be consumed by reacting 5 grams of your copper iron sulfide? Now this problem doesn't explicitly say this, but what is this now? It wasn't before because we were told what about the HCl? It was excess. Now this is a limiting reaction problem. It doesn't say that explicitly, but that's what this is now. We're just using molarity of an acid and mass of a metal, but this is a limiting reactant problem. So this is a little bit of a review here, adding a little bit of new material. So we're going to be solving for our volume. So we're starting off with this concentration, so 6 molarity HCl. So what that means is literally 6 moles per liter of HCl. Kind of scoot this problem down just a little bit if I can, so I can get that balanced chemical equation back in there. Maybe not. Fine, cooperate. There we go. It's crooked, but it'll work. So then, at the same time here, we want to be working for our mass of our copper iron sulfide and get that into moles. So you're going to be starting with your copper iron sulfide. What was this, Blaze? It was 183.
183.525.
Grams. So you're going to go through this chemical equation again, but instead of jumping from your copper iron sulfide over to your dihydrogen sulfide, who are you going to jump to now? Your hydrochloric acid. So your 1 mole is still going to be your coefficient in front of your copper iron sulfide, but now what's the coefficient in front of your hydrochloric acid? 4. So this is going to give us first the moles of your hydrochloric acid. So 3 sig figs, you should be getting 0.109 moles of HCl. And what we can do with this is we need to rearrange your molarity here. Okay, so you can take your molarity here and multiply by moles, right? And that's going to cancel out our moles and just leave us in volume. So if you take 6 molar times 0.109, I'm getting 0.654 liters of HCl had to be used to react that 5 grams of copper iron sulfide. That 0.654, you should be getting something close to that within rounding.
I got like a weighted test.
Okay, what did you get?
I got 0.018.
Was it right?
Yeah.
Did anyone else get that? No?
Number
I made a
6.
stupid mistake.
What did everyone else get for 6? I may have made a math error.
6?
Mm-hmm.
I
Oh,
got
I'm sorry. 7, the volume.
the volume. You mean the end product?
The end volume of your hydrochloric acid, what are you getting?
I
Oh,
got,
no, not 6. Not
I
6,
got-
7.
Oh, 7
I
yeah.
got 0.018
liters. Yeah, that's what I got.
except I did 0.0181 and then I got a total.
I've made a math error somewhere. Hang on a second. Let me redo that. Did you all get this many moles?
You forgot to do the, at the very end,
Oh, I didn't cross
there's
multiply.
1
did I?
liter solution for every 6 moles of HCl.
I didn't cross multiply. That's what I didn't do. That should go in there. So it should be your moles divided by your volume on this one. So, didn't get that answer. Is that what you're getting now? Yeah. Okay. That's my bad. A little bit of algebra error. If you got that or something close to that, you didn't speak up because I make a math error and I don't want you all to like write that down and think that's how it's done. It's not. This should be how you should do this one. So you need to cross multiply there to solve for volume because volume was in the denominator. Otherwise, you're going to
You
get.
said the sig thing was wrong. I got a 0.5 off of that. At the very end, there's no 2.
Oh, yep. So that should be just 0.18.
What's the rule with that again?
So your mass was to 3. So for problem 6, 3 sig figs was okay, but your concentration was only to 2.
So you use the least.
You use the least sig figs when you're multiplying, and you use the least decimal places when you're adding and subtracting. Yep. So that would be 2. So that would be 0.018, not the 2. You drop the 2 because it's not big enough to round that 8 up to a 9. Okay. So. Name, Captain. First, Captain. Who else came in? That I just you're back there. What's your name? Mariah. Long?
Yeah.
Yeah. What's your name?
It's all.
Patrick.
Terrible? Good? Maybe? Sort of? Yeah.
Oh, okay, sorry.